Welcome to Holy Island, an island located along the coast of Northumberland in northeast England. Behind me is a cliff of sedimentary rocks deposited during the Carboniferous over 300 million years ago. In fact, our observations on these rocks show that they were deposited by coastal processes. But before we look at the rocks in more detail, let's go and have a look at a modern-day coastline around Holy Island today. Along the coastline, a number of different processes are in operation, including waves and tides and winds, and also the actions of animals and plants. During this video, we're going to be looking at those processes and seeing what features they form, and then we'll use this information to look at our Carboniferous rocks and see if those are also formed by the same processes. Perhaps the most obvious coastal process is waves. These waves are breaking on the beach and they're transporting sand grains up the beach. Then as they return, the waves have less energy and so the sand grains are deposited. Can you see that the grains here are well sorted, fairly well rounded, and almost entirely composed of the translucent mineral quartz, except for a few dark coloured rock fragments? This is because the high energy action of the waves moving sediment to and fro has sorted and rounded the grains. Fine grain clasts like clay minerals and other physically less resistant minerals will not survive this high energy environment and will have been fragmented and transported further out to sea. Notice how, over time, the breaking waves have built up a slope that dips towards the sea. This is because as the waves break, they have high energy and so they're transporting the sediment towards the land. Whereas when the wave returns, it has less energy, so it's not carrying the sediment back towards the sea. We can measure the angle of dip on this bank using a compass clinometer. And in fact, it's dipping at about 2 degrees towards the sea. This is a much more steeply dipping beach because it's narrower. In fact, it's dipping at about 10 degrees. This area of the beach shows some nice variation in grain size. We've got quite a lot of pieces of coal, some shelly material, and also coarser sand grains. If we dig a trench here, we might be able to see some of the sedimentary structures in the beach below. So let's have a go. So, here is the trench that I've dug. You can see the position of the current day beach dipping gently seaward. And in the trench, these darker layers with the coal in are picking up the former surface of the beach. Notice that they are parallel with the top of today's beach running down, and we call this type of layering planar stratification. This trench has also yielded another feature. If you look just in here, we can see 3 little lenses of black material, and those in fact are picking out the troughs of wave ripples that formed on the beach at that particular time. If you look across the present day surface of the beach now, you can also see the coal in the troughs of those ripples. Down at this end of the trench, we can quite clearly see this very thick layer of coaly debris and also these slightly whiter grains, which are coarser sand grains, picking out this former position of the beach. The water level in the trench, of course, gives us our horizontal level, so you can clearly see that these beds are dipping relative to the horizontal towards the sea. In another trench further along the beach, slight variations in the grain size of the sand clearly show that the sand is planar stratified on a fine scale. Planar stratification is one of the pieces of evidence that we could look for in the rock record to help deduce the possible depositional processes and the environment. But not only do the waves influence the sediments here on the beach where they're breaking, they also influence the sediments much further out to sea. Just along the coast from here, we've obtained some underwater footage of this wave process in action. This underwater footage shows the formation of distinct bed forms on the seafloor at about 4 metres depth. These are wave ripples. They form due to the fact that in relatively shallow water, the waves cause parcels of water beneath the surface to move in an elliptical orbit. When this water motion impinges on the seafloor, the sediment is moved around. Notice how the motion continually reworks the sediment, moving it first one way and then the other, as the crest and trough of the wave passes. The frictional resistance of the water causes the size of the ellipse to decrease with depth until there is no water motion. This depth varies according to the size of the waves. The depth to which waves influence the motion of the water under fair weather conditions is called fair weather wave base. Storm waves are much larger and therefore they influence the water and the sediments to a greater depth. This is called storm wave base. We can see wave ripples on the beach that form due to the action of waves when the sea last covered this area. Notice that they have sharp, symmetrical crests and also that the crests split into two. Let's now look at their profile. In cross-section, notice that the wave ripples are symmetrical in shape. Here we are back on the Carboniferous rocks, and in front of me there's a fallen block which shows some ripples. We know that these are wave-formed ripples, like those that we saw on the modern beach, for two reasons. They have nice, sharp, symmetrical crests. We can look at these crests in a bit more detail using this contour tool. Here we can see the nice sharp crest and the curved trough. The second reason why we know that they're wave-formed ripples is because the crests of them split into two. They bifurcate, such as here and also here. Just like those that we saw on the modern beach on Holy Island. This exposure shows a cross-section through some more Carboniferous wave ripples. Notice that the internal laminations dip both towards the right and also towards the left. And this is because sand was deposited on both sides of the ripple. Remember that in the underwater footage we also saw the sand grains being deposited on both sides of the ripple. I've just walked along the coast a little way, and in the cliff behind me we can see rocks of different colours. At the base of the cliff there's grey rocks, in the middle they're a greenish grey, and towards the top they're cream in colour. We need to find out what the reason for this colour change is. What we have here is a very fine-grained sedimentary rock, a mudstone, and it doesn't contain any sedimentary structures. In fact, I think it was deposited in fairly quiet water conditions. I found earlier a fossil. This is in fact a brachiopod, and it tells us that these mudstones are marine, i.e. they were deposited under the sea. The nice preservation of the fossils also indicates that it's fairly quiet water conditions. Turning round to the cliff again, you can see the contact between those grey rocks that we had at the base and the greenish grey rocks above. These greenish grey rocks are composed of sand-sized quartz grains. They are sandstones. They also contain some sedimentary structures. Looking in detail at these sedimentary structures, what we can see is that they're made up of these dome shapes and scoop shapes that show low-angle cross-cutting truncation to each other. In fact, we call this hummocky cross-stratification, and it's formed by the complex oscillatory motion of the waves. However, at the top of this bed, the hummocky cross-stratification has been disrupted by these cross-cutting cylindrical shapes. These are burrows, where animals have colonised the top of the bed during quiet water conditions after it was deposited by the waves. Overall, in this part of the cliff, what we can observe is several layers of hummocky cross-stratified sandstone, each with burrows in the uppermost part, and overlain by a thin bed of mudstone. We envisage that each of these sandstone beds was deposited by high-energy waves during a storm. Then, as the storm abated and quiet water conditions ensued, animals were able to colonise the seafloor and the mudstone was deposited. The next storm brought in another layer of sand, and so it continues upwards, storm after storm, with periods of quiet water deposition in between. So, this colour change from grey to greenish-grey rocks represents a change in rock type and the fossilised position of storm wave base. That is, the depth to which storm waves influence the sediment during storm conditions in the Carboniferous. Another prominent feature of this cliff is the ellipsoid-shaped nodules. These are composed of calcium carbonate and have veins of pyrite. The nodules formed after deposition, when the sediments were buried. Now let us look at the cream-coloured upper part of the cliff around the corner. This exposure shows quite nicely the features in the upper part of the cliff, and there are several important observations that we can make. First of all, notice that the sedimentary structures are much larger in size. Here we have one of those scoop shapes, and it's about 1 metre in diameter, rather than about 10 centimetres like we saw in the lower part of the cliff. Also, what we have here is actually a sandstone. There's hardly any mudstone in it at all. And the third observation that we can make is that there's hardly any burrows in this. So there's no chance for the organisms to rework the sediment. What we can see here are wave ripples again. Notice their symmetrical shape and their sharp crests. In this case, we can see no internal cross-cutting relationships, and this indicates that these sediments built up constantly through time with no erosion. Notice how the size of the wave ripples on the modern-day seabed is very similar to those that we found in the rocks. So why do these upper sandstones contain larger scale structures and hardly any mudstones or trace fossils? All of these features point towards the fact that these sediments were deposited under high energy conditions in shallower water than those below, and we think that they were deposited above fair weather wave base. That's the depth to which waves influence the sediment under fair weather conditions. The sediments were constantly being reworked by waves, so that the clay minerals have been carried away offshore and there is no chance for animals to burrow the sediment. Do you remember that on the modern day beach, the action of waves breaking had produced a gently dipping bank seaward? And when I dug a trench through that bank, we found that the sands were planar stratified. Here, in these carboniferous rocks, above the complex cross-stratified strata that we've just seen, what we can see is these thinly bedded horizontal units. So these again are planar stratified, and what in fact we think this represents is a beach that formed in the Carboniferous over 300 million years ago. If I look at a sandstone from this locality, we can also see that the sand is well sorted and well rounded, and that there are hardly any clay minerals in it. The second process that I'd like you to consider is tides. You're probably familiar with the fact that the tide comes in and goes out about every 12 hours. On beaches such as these, it's actually quite difficult to see the evidence for tides because the wave processes are so strong. One line of evidence that we can see is strand lines such as these, where we've got lots of shelly debris and bits of coal that have been left behind by the last high tide. What we really need to do is to go somewhere where the wave processes are not as strong and see if we can find any evidence for those tides. And in fact we can do that on the west side of Holy Island, where it is protected. So let's go and have a look. On the causeway to Holy Island, we can observe the tide going out, and what a dramatic change it is. After the tide has gone out, we can see that there is a complex system of channels, sandbanks and mudflats that have been shaped by tidal processes. Down here on the side of this main tidal channel, we can see that the tide coming in is creating a current, and that's transporting sediment and making ripples on the surface of the channel bed. Whether or not current ripples form is governed by the current speed, depth of water and grain size. In this case, the conditions are just right, and the sediment is being picked up and transported along the side of the ripple that dips at a shallow angle and then deposited on the steeply dipping side. Watch the white shell. Notice how it is progressively buried as the bed form builds forward in a down current direction as sand grains are deposited on the steeply dipping side of the ripple. If we were able to cut a cross section through these ripples, we would be able to see inclined surfaces representing the former position of the steep side, just like this. This is called cross-stratification, and we can use its presence as evidence for currents. However, currents do not just form due to tides, they also form under many other conditions. So let's go and look for some more evidence and see if we can find something that definitely indicates tides have acted. Over here we've got a much better piece of evidence that tidal processes have deposited these sediments. At the bottom of the cliff we've got sands with burrows in it, but at the top of the cliff there's a mud which has several layers within it, and this shows that the amount of energy has changed between relatively high energy to a period with lower energy conditions. I wonder how many different layers of mud there are in there, and if that might fit with our tidal cycles. Let's count them and see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. One of the main consequences of tidal processes is that the current speed varies with every tide. When the current speed is at a maximum, sand is transported. As the current decelerates, sand and then the finer-grained mud is deposited. This would explain each of the thin mud-sand couplets. There are, of course, 2 tidal cycles a day, so that is probably why the mud drapes appear to be paired. Over the lunar month of 28 days, the tidal range varies, with the highest range on the new and the full moon, giving us the so-called spring tides, and the lowest on the half moons, giving us neap tides. So the 14 mud layers could well represent deposition during deceleration of the tidal current twice a day, for the 7-day period of neap tides. The thick sandbed at the base of the cliff probably represents the higher energy deposits of a spring tide. The important features of tides is that the main flow direction of the current reverses during the tidal cycle, that the energy changes from high to low, and that the magnitude of the tides varies over the lunar month. So what evidence for tidal processes can we find in the rock record? This exposure of Carboniferous rocks shows cross-stratification. It's inclined in this direction, indicating that as ripples were migrating this way, sediment was being deposited down the steep slope, giving us this cross-stratified unit. Over here, we have a very interesting feature. Again, in this bed, we can see units that are inclined in this direction, indicating that the current moved this way. Whereas in the upper part, the beds are inclined in this direction, indicating that the current moved this way. So within this one unit, what we have is 2 opposite current directions, and this certainly could be explained by the sediments having been deposited in a tidal channel where the current has changed direction. These rocks show a feature very similar to one of those that we saw in the tidal channel. In the lowermost part, we have a sandstone unit. In the uppermost part, we have a unit which is much richer in mudstones. And in fact, we can see that there's several different layers of mudstones. I wonder how many mudstone layers there are. Let's try counting them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 layers. So we have 14 layers in total. How does that compare with what we saw in the tidal channel? There was also 14 mud layers in the bank of the tidal channel, so we could explain the mudstone layers in the rocks in the same way. This exposure shows again evidence of tidal processes. The lowermost part shows lots of thin clay drapes like those that we've just seen. They were probably deposited on a tidal flat. The overlying unit is cross-stratified. But we can tell more than that from this cross-stratified unit. Notice that over here, the layers are very close together. It's quite thinly bedded, and we've got little dark mud drapes on it. As we move in this direction, the layers become further apart, and we've got more sandstone units. And then again in here, the clay drapes are very close together. Over here, where the layers are close together, would be neap tides. In here, where we have thicker sandstone units, spring tides. And here, where the beds are close together with these clay drapes, again the neap tides. And in particular here, you can see that the dark layers, the clay drapes, get further and further apart as more sand comes in and we go into the next unit of spring tides. Wind processes can also be important along the coastline. Here is a distinct crescent-shaped dune beginning to form in the dry sand on the beach below high tide mark. But it will only be temporary because when the next tide comes in, the sand will be reworked by wave processes. However, above high tide mark, sand dunes have built up due to wind transporting dry sand in a landward direction. Importantly though, the biological process of colonisation by grasses has stabilised the dune and prevented the sand from being blown away altogether. Each of the layers in the dune represents the deposition of more sand and its subsequent colonisation by grasses. The final process that I'd like to consider, besides the action of waves and tides, is biological processes, the actions of animals and plants. Here at the strand line, we've got various shells. We've got some bits of crab, some bivalves, some sea urchins, and also some gastropods. But this material has been washed in, transported to this position. And what we really want to know is what's actually living in this high energy beach. Peter's digging just over there, so let's go and see what he's found.
Yeah.
So, what have you found?
Well, we got this little worm here. He's trying to get away. He's trying to burrow into the sand at the side, but they're pretty active, you see.
Yeah.
And there's one here. These are little polychaete worms, little bristle worms. They can move through the sediment pretty rapidly. And look at these bivalves here. There's some of them, obviously, are just, I'll just give it a wash. Some of these are clearly just single valves of dead bivalves. But interestingly, we got quite a few living bivalves here. They've got both their valves together, okay? And look at that, the blade shape of it.
Yes.
These little things are well adapted for slipping through the sediment at high speed, like a hot knife through butter.
Amazing.
So they're very well adapted to these shifting sands. And although the surface may look quite barren, actually there are obviously plenty of active burrowing creatures living beneath it, but they don't leave much trace of their activities behind because the currents just keep reworking the sand all the time.
So they're constantly moving around?
They're constantly moving around, yep.
On the landward side of the tidal flats, we find an area that again is stabilised by vegetation. We have plants like this succulent here and these grasses which are tolerant to the salty conditions as the tide comes in every day. If we go over here and look at these muds, what we can see is that in fact the muds are very black in colour, indicating the amount of plant material that's actually in there. And also burrows left by worms. So let's have a look at our Carboniferous age rocks and see if we can find any evidence for biological processes there. Here are some sandstones that were deposited in high energy conditions in a beach environment. But the bed just up here shows no sedimentary structures in it at all. Let's go and have a look at the top surface of that and see what we can find. Ah, we have on this top surface is the remains of fossilised plants, including this root-like structure here. During the Carboniferous, this was a swamp-like area, but all that remains today is the sandstone bed, which represents a fossilised soil, and these plant fossils. Here is some more evidence for biological processes. These are burrows, and they indicate that animals were living in these sedimentary deposits during the Carboniferous. Burrows are common in the rock record. That concludes our introduction to coastal processes. What I've aimed to do in this video is to demonstrate that by making careful observations on sedimentary rocks in the field and by understanding what is happening in modern day settings, we can really begin to understand what sedimentary processes are responsible for the deposition of particular sedimentary rocks. This enables us to go on and deduce the possible depositional environments of the rocks.